any questions that you have, please never hesitate to ask, okay? All right, this is AB Calculus week number 2. Obviously, week number 1, you guys had some work to do. It was dealing with limits. We're going to be dealing with limits again today. For like the next 3 weeks, we deal with limits and continuity and stuff like that. It's pretty, I like this stuff. It's not the hardest stuff in the world. I'm just going to skip through this stuff because we have a lot to go through today. This week and next week, we have if you take a look at the PACE chart last week, I can define limits using limit notation. I can estimate limit values from graphs and tables. We'll discuss that a little bit today. And then today, we're also talking about I can determine limits using algebraic properties of limits, okay? That's a little bit tougher when you're dealing with properties of limits to find the limits, but I think you guys will be just fine. First thing I want to do is I want to play a short video on what is a limit. I think this calculus site really does a nice job on explaining. So I'm going to have to share an application screen here. Now, this is going to be limits and continuity, limits and continuity. How do I evaluate limits? When does a limit exist? Okay, this one right here, lesson 1. So I'm going to share that, okay, and then I'm going to play this. 1 second here. I just want to make sure you guys can see what I'm seeing. Okay, so now I'm going to play that. Hopefully the volume will be good enough.
Talk about limits, but the plain fact remains, most people don't understand what a limit is. So for now, we're going to focus on what is a limit. In basic terms, a limit is a height that a function intends to reach. That's pretty important, so let's say it one more time. A limit is the intended height of a function. Now, this might give you pause. You might think, how am I supposed to know what height a function intends to reach? I don't even know what my intentions are most of the time. How am I supposed to discern the intentions of a function? That's a good question. And the fact that you don't understand exactly what I'm talking about is because all of the functions you've been dealing with, or at least most of them, have had their intentions completely clear. If a function intends to reach 3, it reaches 3. If a function intends to go 6 units high, it goes 6 units high. There hasn't been a lot of mystery so far. So I understand that you might be a little confused, but you've dealt with function heights a lot. So we might as well review function heights a little bit and then get into exactly what I mean by intending to go to a certain height. Let's start by looking at a very simple function graph. What I have here is the function f of x equals x squared, basic parabola. You'll notice that the function changes heights all throughout its domain. That's a very fancy way of saying that the function reaches many different heights based on whatever the x value you're looking at happens to be. For example, what if I look at the function height that corresponds to x equals 2? Well, it's not very difficult to figure out exactly how high that function is going to be when x equals 2, because all I have to do is plug in that x value into the function to figure out what that height will be. So, if I plug 2 into x squared, I get 2 squared, or 4. This means that the function reaches a height of 4 whenever x equals 2. Pretty simple. But now I can create my first very basic limit statement, and that is the limit as x approaches 2 of f of x equals 4. This just means that whenever I'm getting very close to the x value of 2, my function is getting very close to the height of 4. There's nothing really earth-shattering about what we just learned. But that changes when we examine functions that do not reach the heights they intend. Take, for example, this function. G of x equals the fraction x squared minus 6x plus 8 divided by the quantity x minus 2. Here's what the graph looks like. It looks like a plain old line. Or does it? If we zoom in, you'll see that it has a hole in it at the coordinates 2, negative 2. The hole exists because plugging x equals 2 into the function results in 0 divided by 0. And we know that dividing by 0 is a very bad idea. It breaks mathematical laws that we really can't even get into here. However, though this graph has a hole in it, it still possesses a limit when x equals 2. Clearly, the graph intends to reach a height of -2 when x equals 2. Even though that graph doesn't actually reach that height, it doesn't matter. The limit still exists, and we can say that the limit as x approaches 2 of g of x is equal to -2. This begs the question, when exactly does the limit exist? We examine that in the next module. Now you have some idea.
Okay, so now the concept here is trying to find the limit as a function goes up. I think I'm gonna jump around to slides today. Okay, so let's try this function right here. Okay, so if I write a function notation, and function notation, it looks like this. It'll be the limit as x approaches, and then there'll be a number. So let's say I said the limit as x approaches 2. Okay, so if you're looking at this graph, what is the limit as x approaches 2? Okay, and this is a question for you guys. What should the limit be as x approaches 2 of this graph? 4. I agree. The height of that function when x equals 2 is equal to 4. We can see that over here. It equals 4. Now, you can write limit notation two different ways. Well, I'm sorry, you cannot write it two different ways. So sometimes we ask, what is the limit as x approaches from the right-hand side? So let's say I ask you, what is the limit as x approaches 0 from the right-hand side? Okay, so what you do is you start way over here, you go from the right-hand side. What is the limit as x approaches 0 from the right-hand side? Okay, so take a look at that graph. What would the limit be as x approaches 0 from the right-hand side? 4? I disagree with that. Here is 0. Okay, this is 0 right here. So I'm coming toward 0 because it says the limit as x approaches 0. There you go. The height is 2. So now I could say, okay, the limit as x approaches 0 from the right-hand side is 2. What is the limit as x approaches 0 from the left-hand side? So that's what that little negative says. It says, hey, we're coming from the left-hand side now. Well, I don't even know what it is. I don't know. Let's say that this graph goes up here and it comes down like this, okay? So this other blue line here, let me put it in red so you can see a little better. So now, let's say that this is the graph coming from the left side. So what would the limit be as x approaches 0 from the left-hand side? 6. Absolutely. Now, the definition of a limit says that the limit as x approaches some number, it doesn't really matter what the number is. So the limit as x approaches 0 and the limit as x approaches 0 from the right and from the left has to equal the limit as x approaches 0. That means the limit does exist. Okay, now, this is a really key point here. If the limit from the left and the right are not the same, okay, then the limit at that point does not exist. So in this problem, if I said, what is the limit as x approaches 0? It does not exist. Why? Because when you come from the left, you get 6 for your limit. When you come from the right, you get 2 for your limit. They are not the same. That means the limit as x approaches 0 does not exist. Okay? That is a very, very important point, and I'm going to show you another short video. Okay? let's see here. Do I have the second one here? Okay, so let's go to another video, because I think this guy does a really good job of explaining what things are. Okay, so I'm going to go to tab again. All right, so here we go.
Some idea of what a limit is, and we need to talk about when does a limit exist. To illustrate my point before we get started, let's set up an example. Let's say you and a friend are going to meet for dinner, and you're meeting at a diner that's centrally located between the two of you. If you live east of the diner and your friend lives west of the diner and you both want to drive to meet there, ideally, the roads which lead to the diner will lead you to the same place. If you travel towards the diner from the right or east, and they travel towards the diner from the left, you should meet up in the same place. Mathematically, this is basically what a limit is. A limit exists if you travel along a function from the left side and from the right side towards some specific value of x. As long as that function meets in the middle, as long as you arrive at the diner, as long as the heights from the right and the left are the same, then the limit exists. Now it's time to get down to the brass tacks and look at this mathematically. Take a look at the graph of this function f of x. Visually, you can see that it's got a break in it at x equals 4. So, if we travel towards 4 from the right, we will arrive at a height of 2. However, if you travel towards 4 from the left, you will arrive at a height of 1. This means that no limit exists for f at x equals 4. Let's go back to our diner metaphor for just a second. Notice that as I'm traveling along the road from the right, I end up at a height of 2. But if you travel along the road from the left, you end up at a height of 1. These heights don't match. We won't both arrive at the diner, and no limit exists. We call the height at which we arrive from the right the right-hand limit of f of x, as x approaches 4 from the right. And we denote this with a little plus sign in our limit symbol. Our height that we arrive at from the left is called the left-hand limit of f of x as x approaches 4, and it is denoted with a little negative symbol. Mathematically, in order for a limit to exist, both the right and the left-hand limits must be equal. Now let's change this function just a little bit. This new function, we'll call g of x, does possess a limit. Can you see why that's the case? It's because the function no longer has a break at 4. Now, there's something to be said here. The previous function did not have a limit at 4. It did have a limit at many other points. For example, a limit existed at 1, at 2, at 5, at 0. All these x values showed locations where the graph did not break. In essence, a graph will not possess a limit if it breaks at the given x value. That's why our new function does possess a limit at x equals 4. Now, let's go back to our diner example one last time. Let's say we're traveling towards the diner. We both arrive at the same location, but the diner isn't there. Maybe it's caught fire or something. Does that mean the limit doesn't exist? The truth is, the limit will exist even if the diner's not there, because you still arrived at the same place. In other words, mathematically, a limit can still exist if your destination is a hole in the graph, because it doesn't matter whether or not the point is actually there. What matters is that you arrived at that point, coming from the right side and the left side. In conclusion, a limit exists on a graph if you arrive at the same height coming from both the right and the left side of the given x value.
Every vacation at a verbal home needs someone like you, who knows that.
Okay, so now that we have limits, so that basically covered last week, correct? Last week we talked about limits. Now when we're dealing with a table of values, if it asks us for the limit, when you're dealing with a table of values, and then said, okay, what is the limit as x approaches 1? Well, if I'm coming toward 1 from the left-hand side, I go to about 2, right? And if I come from the right-hand side, it looks like I'm going to 2 also. So that means the limit here would be 2, because you can look at a table and figure out what a limit is. As long as it's going to the same thing, it's going to have a limit at that value. So tables are very easy to figure out what the limit is, and a limit is also pretty easy. I think it's easier to find the limit of a graph. I mean, so in this problem, I'm asking what is the limit as x approaches 2. I'm going to ask a couple questions on this problem. I'm going to ask you, what is the limit as x approaches 2 from the right? What is the limit as x approaches 2 from the left? And what is the limit as x approaches 2? Okay, so in this problem, what is the limit as x approaches 2 from the right-hand side? From the right is 1. I agree. What is the limit as x approaches 2 from the left-hand side? 2. What is the limit as x approaches 2? Does not exist. That is absolutely correct, because the left-hand limit and the right-hand limit have to be exactly the same for a limit to exist. Since they are different, the limit does not exist there. Excellent. Okay, now here's a couple problems from the Khan Academy. So it says the function f is defined for all numbers except x equals 3. What is a reasonable estimate for the limit as x approaches 3? So in this problem, what would your answer be? What is the limit as x approaches 3 for that problem? -4. Absolutely correct. Now, when you say, if I asked you, what is the definition of a limit? What I would expect students to say is, it's the intended height of a function. That's what a limit is. The limit of a function is how high is it supposed to go at that given x value. So the second graph over says, what is a reasonable estimate for the limit as x approaches 4? Okay, so what would that be? Does not exist, right? Because it's different coming from the left and right hand side. Good. So limits should be a fairly easy concept. Now this problem here, very similar to a problem on your assessment. This, when it says something like this, the first problem, A, f of -2, basically this is saying, what is the value when -2 is plugged into the function? Well, here's -2, there's no value, so it does not exist. If I asked you what is f of 2, that's what's the value at 2, it's an open dot. That does not exist. I want one that works. Okay, so f of 4, so what is the value? So this is the value at f of 4. It is equal to 2 there. Okay, so that, then there's all these questions. What is the limit of x? What is the limit as x approaches -2? Does not exist, does it? Because it's not the same. Okay, so any questions up until now? Okay, because I want to get to the point where we're solving or we're finding limits using algebra, because that's a little bit harder. Looking at graphs, looking at tables, pretty straightforward. When you start getting into the algebraic ones, it gets a little bit tougher. Here are 3 graphs you need to memorize. Okay, and why do you need to memorize these? Well, because on an AP test, they will give you a problem like this. They'll give you this function and they'll say, what is the limit? What is the limit as x approaches 0? They might, let's go from the left-hand side. Well, if you knew what the graph looked like, you would know what the answer is. Do you guys know what the answer is for that problem? What is the limit as x approaches 0 from the left-hand side? Okay, and that is because you don't know what the graph is. If you knew what the graph was, you'd have no problem answering any limit questions. And every year they use this, one of these functions. Okay, so here's the graph of the absolute value of x over x. Here is 1. Here is -1. The graph looks like this. It's a horizontal line, and over here it's a horizontal line also at -1. And one of them is solid and one of them's a circle. I don't know which one is which. we'll just go that way. Okay, so what is the limit as x approaches 0 from the left-hand side? -1. What is the limit as x approaches 0? Does not exist. Excellent. What is the limit as x approaches 10? One. Exactly. So I could ask you 100 questions using this function, right? But if you didn't know what the graph looked like, you would have a difficult time trying to answer the questions. So memorize this one. This one comes up all the time. So does this one. The sine of x over x. Okay? Here's what that graph looks like. Memorize. And I don't ask students to memorize a lot of things, but boy, does this help out if you can memorize these. All right, so this is the sine of x over x. It's a tough one to graph. Okay, I usually try to do this, and it gets closer and closer and closer to 0. And then it comes down here, and it just keeps oscillating until it gets there. So this is 1 right here. So what is the limit as x approaches 0 of this graph, of this function? It is 1. Yeah, good. Now there's a lot more that I can ask you, but we don't know how to do asymptotes yet, so I'll just leave those other ones. But remember this graph. And then the integer function, that graph looks like it's a step function. Okay, and what does that mean? This is 1, 2, 3. So the graph looks like this. It just keeps going up by ones. Okay, so this one, they would say, what is the limit as x approaches 1? Okay, what's the limit as x approaches 1? 0? Disagree with that. Okay, and the reason is, when you come from the left to 1, it's 0. When you come from the left or the right, it's 1, so it does not exist. Yeah. What is the limit as x approaches 1.5? Okay, this is 1 here, this is 2, so it's 1, right, exactly. So any value like 1.5, 1.6, 1.7 would always be 1, right? All right, so those are 3 graphs that you should memorize. It's going to help you in the long run. You'll be able to look at things and say, oh, that's pretty easy. Okay, finding limits using tables, we did that already. And some examples using tables and stuff like that. Finding limits, evaluating limits by direct substitution. That is the first place you always start when you're trying to find a limit. You would just substitute the number in. So for example, if I gave you x squared minus 4x plus 5, and I said, what is the limit as x approaches 3? First thing you would do is you just plug 3 in here. So you would go, I need to turn my mic on again, you'd go 3 squared minus 4 times 3 plus 5, so 3 squared is 9, minus 12 plus 5, so 9 minus 12, that's -3, so that would be 2. So your limit would be 2. Substitution is always the first way that you try to figure out what the limit is. Now, try this one. Uh-oh, now I'm testing your knowledge on sine, cosine. This one is a good problem. Okay, what is the limit as x approaches 0 of e to the negative x cosine of x? It's good. It's a good problem. Don't know. All right, most kids wouldn't, but it's a pretty easy one if you understand a little bit of concept about cosine and sine graphs. Okay, cosine graph. Here's the cosine graph. Cosine graph starts at 1, then it goes down, and it comes back up, and then it goes here. You should have this one memorized too. This is 90 degrees here. This is 180, and this would, at 180 it's -1. This is 270 here, where it crosses again, and 360. So if I said, what is the cosine of 90 degrees? You should say 0. If I said, what is the cosine of 0? You should say 1. Okay? So now, in this problem, what is the limit as x approaches 0? I would plug 0 in there. What is anything to the 0 power? What is anything to the 0 power? 1 is correct. And what is the cosine of 0? Well, if I look at my graph, it looks like 1. That's my answer. The limit as x approaches 0 of e to the negative x cosine of x is equal to 1. Pretty awesome problem. Now, this problem down here, you plug in a 4 here, we get x squared minus 4 over 4 minus 4. Well, that's 0. You can't divide by 0, so most kids would say does not exist. I disagree with that answer. Okay? And the next video is going to tell us why. All right, so I'm going to play another short video about finding limits using algebra. Okay? Now, we did not scare away Carol. She had to leave early today. She had another meeting, so we not scare her away. She just had to leave a little bit early today. All right, so let's see here. Share application screen. I'm going to do another video here. All right, how do you find a limit?
Or not a limit exists. The next logical step is to try to figure out what the heck that limit is. So that's what we'll be focusing on in this section. How do you find a limit? The fancy word for finding the value of a limit is evaluate. So when you see the directions evaluate, basically you should be expecting to get a numerical answer. There are 3 major ways to evaluate a limit. They are substitution, factoring, and the conjugate method. We're going to go ahead and start with the easiest one, which is direct substitution. It is just as easy as it sounds. We'll take an example. Here's one. The limit as x approaches 0 of the fraction x squared minus 1 divided by the quantity 2x plus 3. In order to evaluate this limit, all you've got to do is plug in 0 everywhere you see an x. So we'll put in 0 in the numerator and in the denominator, and we end up getting negative 1 divided by 3. So our limit is negative 1/3. It's as easy as that. Unfortunately, not all limits are this easy. And you've already seen one for which that's the case. Remember that function that we were dealing with in the first section of this chapter? In case you don't, here it is again. The limit as x approaches 2 of the fraction x squared minus 6x plus 8, all divided by the quantity x minus 2. We looked at this before. It had a hole in it at the coordinate 2, negative 2. And we concluded from that the intended height was negative 2, making it the limit. However, it would be nice to be able to figure out why this is true mathematically. And to do that, we'll have to use the factoring method. As you can see, and as we saw before, direct substitution results in 0 divided by 0, which is not allowed. So we'll have to resort to this new method. We'll use the factoring method because the numerator of this fraction is factorable. If we factor it, we'll get x minus 4 times x minus 2. Can you see why that's a good idea? Well, the reason is because now the numerator and the denominator both contain the term x minus 2, which I'm going to cancel out. This leaves the limit as x approaches 2 of x minus 4. This is much simpler to solve because now you can use substitution. And when I do, I get 2 minus 4, which is equal to negative 2. Remember, we knew the limit was going to be negative 2, and we're right. Feels good to be right. If the substitution method fails and the factoring method fails, you're not without hope. You can still try the conjugate method. Before we talk about the conjugate method, though, we might as well figure out what a conjugate is first. Take a look at this expression, the square root of x minus 4. Now, this is a plain old two-term expression. However, it is easy to make a conjugate. All you do is change the negative sign in the middle to a positive sign. The conjugate of the square root of x minus 4 is the square root of x plus 4. That's all there is to it. Now, What if you see an expression like this in a limit problem? For example, this limit problem. The limit as x approaches 16 of the fraction, the square root of x minus 4, divided by the quantity x minus 16. Well, what we'll do is multiply the top and the bottom of the fraction by the conjugate of the radical expression, which, as we said, was the square root of x plus 4. Now,
Okay, I'm going to stop him there because I don't like the conjugate method, okay? And I'll show you why I don't like it. He makes it way harder than what it's supposed to be. If you use this one little rule that most students don't realize. Let me see here. I'm trying to find a short or a page that has a lot of blank space so I can work on it. So here, not enough room. Okay, let's go down here. Okay, so this is the problem that he was working on. He was working on this problem where it said, I think it was the limit, I don't even know what the limit was. It must have been the limit as x approaches 16 of the square root of x minus 4 over x minus 16. That's the problem he was working on. If you put 16 in there, you get 16 minus 16, which is 0. Can't do it. Got to find a different method, okay? Now, if I asked you what x squared minus, let's say, 16 is, do you know how to factor this? How would you factor a problem like that? It's a difference of two squares. Okay, so what would it factor down to? It would just factor down to x plus 4, x minus 4, okay, or x minus 4, x plus 4, okay? I agree. Is this the difference of two squares? Is that the difference of two squares? X minus 16. Ah, but what is the rule? The rule says that you just take the square root of both terms, right? Isn't that how you factored? You took the square root of this term, you took the square root of this term. Well, why can't I take the square root of this term? That gives me the square root of x minus 4 times the square root of x plus 4. And do you see how easy that is now? I just factored this. Now the x minus 4 on top and the x minus 4 on bottom is going to cross off. So I'm just left with 1 over the square root of x plus 4. If I plug 16 in now, the square root of 16 is 4. 4 plus 4 is 8. My limit for this problem would be 1/8. Boom, done. And that, once you understand that everything that has a minus sign in it is a difference of two squares, you can factor anything down that has two things. Yeah, that makes it really quick, really easy to do. All right, so let's go back up, because now we're dealing with solving limits using algebra now, okay? There's a couple problems like this using algebraic properties. Did I have the rules? Okay, here's the rules. You know, if you have a limit and you have a number in front, you just multiply the limit by that number. So if I asked you, what is, turn my marker on every time I switch screens, which is a little crazy. So if I asked you, what is the limit as x approaches 4 of x squared, and then I put a number in front of here, we would just find the limit. So that would be 16, and we'd multiply by 5. Boom, we'd have our answer of 80. Done. So all of these limits are very straightforward. If you're multiplying or if you're adding, subtracting, you can add limits, you can subtract limits, you can multiply limits, does not matter. So if I gave you a problem like this, and it said functions f and h are graphed, then they want you to find the limit as x approaches -3 of f of x plus h of x. So, okay, well, here's f of x. -3, the limit is, of -3, that does not exist. So this does not exist. Okay, so if that does not exist, I don't know if you can add a number to something that does not exist. So I would say the answer would be does not exist, because one of them doesn't exist. Let's see if this one makes any more sense. This is really a composite function. So the first thing I have to do is I have to find the limit as x approaches 2 of g of x. Holy cow, that does not exist either. Wow, these are some really bad problems, because that's going to be does not exist. So that's going to, whoa, I should have looked at those problems before I put them on there. I would say both of the answers are does not exist. Yeah, interesting. So let's try one that does exist. Let's say I asked you to find the limit as x approaches 2 of f of x plus h of x. Okay, so I'm using these functions here. So x approaches 2 for f of x would be 1, so I would just put 1 here, plus, if I wanted to find the limit as x approaches 2 of this one, that's 1 also. So my answer would just be 2. Okay. Now, if it was something like this, if it was the limit as x approaches 2 of 3f of x, well, again, we just find the limit as x approaches 2 of f of x, which is 1, and then just multiply by 3, and my answer would be 3. So if they give you a problem like that, super easy to find. All right. What is each one of these limits? Well, when we find limits, we always use substitution. That is our first step. So if I put 2 in here, I get 6 plus 5, that's 11. If I put 8 in here, do you know what the log base 2 of 8 is? Make those brain cells work. Okay, should be 8, because when you have a log, so if I have the log base 2 of 8 is equal to, you really ask yourself 2 to what power is equal to this number? Okay, 2 to what power is equal to 8? So 2 to the third is equal to 8, so that is 3. Okay, and then this one, I just put 1 in here. 10 times 1 is 10, minus 1 is 9. The square root of 9 is 3. Done. So the first thing when you're trying to find the limit, always just plug the number in. Substitution method. Now, substitution doesn't always work. Substitution is going to work in these. I can tell because it's just a function and a function. Now, this problem here, it says find the limit as x approaches -1. Okay, well, when x is less than -1, we would use this function. When x is greater than or equal to -1 and less than 0, we would use this function. So this is it's called a piecewise function, so I would use this function in order to find my limit, because it's in the interval. So if I put -1 in here, -2, so my answer would be -1. All right, so if you ever divide by 0, you're going to have to try something else. For example, this problem here. If you put 3 in here, you get 9 minus 12 plus 3, which is 0 on the bottom. That means I have to try something else. It's divided by 0, can't do it. This one's going to be 0 divided by 0. But anytime it's divided by 0, you want to try something else. My first step is always try to factor. So x minus 3, and then x squared minus 4x, so that's going to be x minus 3x minus 1. And what happens is the x minus 3's cross off, so I'm left with 1 over x minus 1. Now I can plug in 3. So this is going to be 1 over 3 minus 1, so 1/2. So my limit is going to be 1/2 there. So whenever you plug in a value and it becomes a 0 in the denominator, you can't stop. You cannot just say, oh, it does not exist. You have to try to factor down. Okay, so this one here, the top factors to x minus 3x plus 3. And the bottom is x plus 3. So guess what? Those cross off. So now if I plug in -3, -3 minus 3 is -6. So my limit as x approaches -3 should be -6 there. All right. I've been talking a lot. Any questions on any of this stuff? Is it making sense? Are you totally lost? Or are we good to go? Awesome. Very nice. Okay. And then the last, this looks like they, oh, I see a little square there. Makes a whole lot of difference there. So let's erase this. Okay, so in this problem, it says, what is the limit as x approaches 3? Well, if I plug 3 in here, 3 minus 3 is 0, 0 squared is 0. So I can't, so I'm going to have to use some algebraic steps to solve this. So I'm going to factor this, x minus 3, x plus 3. And then I'm going to, I'm just going to write out x minus 3 squared, because that's going to be x minus 3, right? So this crosses out. All right, so now I'm going to put 3 in again. Well, I put 3 in here, and I still end up with 0 on the bottom. And I put 3 up here, and I end up with 6. So this is 6 over 0. There's nothing I can do anymore. I still have 0 on the bottom. There is nothing I can factor out. There's nothing I can do. So that means when I graph this thing out, there is going to be an asymptote there. It's not going to, for example, there's going to, like if you graph this thing out at positive 3, it's going to be an asymptote. So this thing is going to look something like this. So the limit does not exist for that problem. Whew, that is the last slide for today. Got through it a lot quicker than I thought, especially even showing the videos. I thought showing the videos it would take too much time. All right, if you ever have any questions or concerns, please never hesitate to email or call me. I'm always willing to work with calc students. All right, have a great evening and rest of the week, and I hope to see you back Monday afternoon from 2 o'clock till 3 next week. All right, bye.